formula for core resistance, often denoted as RC, allows us to determine the effective resistance representing core losses in an equivalent circuit model. This resistance is expressed in ohms. The formula itself is RC equals the quantity Vm squared minus Pout divided by PCU. Let's break down each component of this formula. Firstly, Vm represents the maximum core voltage. This voltage is the peak voltage experienced by the core material during operation. Its unit of measurement is volts. It's crucial to use the maximum voltage, not the root mean square, or RMS voltage, as the core losses are directly related to the peak magnetic flux density, which in turn is determined by the maximum voltage. Secondly, Pout stands for the output power of the circuit. This is the useful power delivered to the load connected to the circuit. Its unit of measurement is watts. The output power must be accurately determined to ensure correct calculation of the core resistance. Thirdly, PCU refers to the core loss power. This represents the power dissipated as heat within the core material due to hysteresis and eddy current losses. It's also measured in watts. Determining PCU accurately is critical, but it's often the most challenging aspect of calculating core resistance. The core loss power, PCU, is typically not directly measurable in practical situations. It must be estimated using appropriate methods. One such method is the Steinmetz equation. The Steinmetz equation is an empirical formula that relates core loss to the magnetic flux density, frequency, and core material properties. The general form of the Steinmetz equation is PCU equals K times F to the alpha power times B to the beta power times the volume of the core, where K, alpha, and beta are constants that depend on the core material. F is the frequency of the applied voltage. B is the maximum magnetic flux density. And the volume of the core is the physical volume of the core material. To use the Steinmetz equation, you need to know the specific Steinmetz coefficients for your core material. These coefficients are usually provided by the core manufacturer. Additionally, you need to determine the maximum magnetic flux density B, which can be calculated using the following equation: B equals Vm divided by N times A times omega, where Vm is the maximum voltage. N is the number of turns in the winding, A is the cross-sectional area of the core, and omega is the angular frequency, which is equal to 2 times pi times the frequency. If the Steinmetz coefficients are not available, you may need to rely on empirical measurements. Empirical measurements involve directly measuring the core loss under different operating conditions and then using the data to create a curve fit or lookup table. This method can be more accurate than using the Steinmetz equation, especially if the core material is not well characterized. The process of empirical measurements typically involves the following steps. Firstly, construct a test setup. You'll need to build a test circuit that allows you to apply a known voltage and frequency to the core material. This circuit should also include instrumentation for measuring the input power, voltage, and current. Secondly, apply a range of voltages and frequencies. Vary the applied voltage and frequency over the range of expected operating conditions. At each operating point, record the input power, voltage, and current. Thirdly, calculate the core loss. The core loss can be calculated by subtracting the copper losses in a winding from the total input power. The copper losses can be calculated using the following formula: P copper equals I squared times R, where I is the current and R is the resistance of the winding. Fourthly, create a curve fit or lookup table. Use the measured core loss data to create a curve fit or lookup table that relates core loss to voltage, frequency, and other relevant parameters. This curve fit or lookup table can then be used to estimate the core loss under different operating conditions. It's important to note that the accuracy of the core resistance calculation depends heavily on the accuracy of the core loss estimation. If you have access to detailed core material specifications and can accurately measure the operating conditions, you can obtain a reasonably accurate estimate of the core loss. However, in many practical situations, the core loss estimation may be the dominant source of error in the core resistance calculation. Once you have determined Vm, Pout, and PCU, You can plug these values into the formula RC equals the quantity Vm squared minus power divided by PCU to calculate the core resistance. The resulting value of RC represents the effective resistance that accounts for core losses in the equivalent circuit model. This resistance is placed in parallel with the magnetizing inductance in the equivalent circuit. The core resistance is an important parameter for modeling the behavior of magnetic components such as transformers and inductors. It affects the efficiency, voltage regulation, and overall performance of these components. A high core resistance indicates higher core losses, which leads to lower efficiency and increased heating. In summary, the formula RC equals the quantity Vm squared minus power divided by PCU allows you to calculate the core resistance in an equivalent circuit. This resistance represents the core losses and is an important parameter for modeling the behavior of magnetic components. Accurately determining the core loss power, PCU, is crucial for obtaining an accurate value of RC. The Steinmetz equation and empirical measurements are two common methods for estimating core loss power. Remember that the accuracy of the core resistance calculation depends heavily on the accuracy of the core loss estimation.